So this is a little bit stronger in terms of bond strength. And I don't know if this is confusing at all. We don't necessarily have to think too deep about it, but it helps. Because now think about it like this. We are dealing with water. So how come, so think of that now. If we think of an acid put in water, think about that scenario, think about the polarity of water, and think about this, and then think of that and say, okay, how come HBRO dissociates when we put it in water?
Well, thinking about the polarity of water, we know that overall it's neutral, but it definitely has partial positives and partial negatives. And because of that, it's going to attract the partial positives where it's partially negative. And so whenever you attract an extra hydrogen, that's where we get the H3O plus, the hydronium ion, because the charge is going to attract it and it's going to break the bonds. The charge is stronger than the bond.
Right. Very good. So we have this. The electrons are going to come from this to this, and this electron, these pairs are going to grab this H, thus forming the hydronium, right?
Yes. That is so cool.
So that's kind of the idea, right? And we have now a positive because it's got a proton. So the reason why acids function the way they do is because we're sticking them in water. So this particular compound has certain properties with its electrons, its electron configuration, and its electron density. The way that it functions in water is that the water will yank that H off. The stronger the acid, the more that this water will pull it off as well. The more that this compound will give away its H to water to form hydronium. Now, and it would also be true in terms of a strong base. A strong base is just opposite, where if we stick something like this in water, this is a strong base. Now, you don't necessarily have to memorize this, but anyways, if you stick this in water, it will want to, it kind of looks like this, I guess. But O, and, oh man, how would that look? It's kind of a weird one. O2 minus has just got an extra electron in there. Okay, anyways, it would want to steal this and pull it towards itself, right? Leaving behind an OH and forming water here, because that would make water after that. But so an OH then is what is made when a base is put in water. And so, and of course that's just the other idea of this particular compound, this base, really likes to accept protons. So when you stick it in water, it does that because of the conditions of water and just kind of how it is, you know. Just, I don't know. So that's important to realize, because as you're doing acid-base chemistry all along, I mean, you're just dealing with water every time. Always dealing with hydroniums and hydroxides. As a result of the acid either giving more H's to the water or taking them away. So I kind of spend time on that because it's going to help a lot. Yeah. Especially because this is all acid-base chemistry is. I mean, just that idea of proton donation, proton taking, receiving. So the strategy then of approaching this is thinking, okay, well, how much is this really going to dissociate? Well, you just spent all of chapter 14 talking about a way of analyzing equilibrium. And the best way that I have found is using an ice table. Mm-hmm. So you do the same thing with acid-base chemistry. The thing that I would do is say, okay, well, we have this particular compound. We're sticking it in water. We're going to have to get the table. Do you have the... You have the table? Oh, yeah, you already pulled it up. Let's see, we have 0.01 molar of this stuff. So we have 0.01 molar of HBRO that we put in. And so if you looked at the outside of a bottle, I mean, like in the chem lab or something, I mean, you would have your little bottle here, and it would have on the outside of it, say 0.010 molar of HBRO, right? But that doesn't necessarily tell us exactly what's happening inside of this. Because it's not just this much of HBRO just floating around in there. It's reacting with the water, right? It's in this equilibrium, right? So constantly HBRO is reacting with water to make this. And then because this is a base, the BRO minus is grabbing hydronium or water and turning it back into an acid, right? So it's just going back and forth. The question is, how much does it do that? So that's why we use an ice table, and I'm sure you learned this in class. And with water, we can ignore it because it's a liquid. And so I just put a little line through it. And we simply use the same things, the same strategy, minus x plus x plus x, right? And eventually you probably won't even need to do this anymore because you'll get really good at it. You won't even have to draw the ice table. You notice now that we have an equilibrium with certain variable we need to solve for. And so we use the table to get our K value. So what is it?